各位老师、各位同学，大家好，非常欢迎来参加这礼拜一的 Crossfit。那我们今天非常荣幸可以邀请到李文金教授，他目前是 Kansas University 的特聘教授，然后他也曾经是我们一个中心的主任。那今天非常开心可以邀请他来给我们分享。那他的题目是 various aspects of hypergeometric functions， 我们热烈欢迎他。
非常荣幸跟非常高兴，今天能有这个机会来再度访问清华大学，看到这么多老朋友，然后来跟大家分享我最近学的一点点东西，这个 hypergeometric functions。那这个 hypergeometric functions 一开始 ，should I use English？ Okay, so it was introduced by Euler, but Gauss was the first person who studied this topic systematically. And at the time, the hypergeometric functions they studied has three parameters, a, b, and c, which are complex numbers, and the function itself is defined as a power series. Okay. So the coefficient is that you see this a bracket r, this is a Pokehammer symbol. It means a times a plus 1 times a plus r minus 1. So it is gamma of a plus r over gamma a. So it's a product of a bunch of the product and quotient, a bunch of gamma functions. So in particular, 1r here means that it's r factorial. Okay. So as you can see that from the ratio test, the function converges when absolute value of z is less than 1, provided that the coefficients are well defined. And you can see that if c is a negative integer, then when the r is large enough, somewhere we'll get a 0 here, so we have 0 in the denominator. That's not allowed. Okay, so just keep in mind that hypergeometric function is defined whenever the denominator is non-zero. Okay. So likewise, when a or b is a negative integer, then the numerator will be 0. Then this infinite series becomes a polynomial. Okay. And if that happens, we say that this hypergeometric series terminates. And there's another special case is when a is equal to 1 and the b is equal to c, so you can cancel the part from b and the c, and so the coefficient is equal to 1. So in this case, the hypergeometric series becomes the geometric series. So the geometric series is a special case of a hypergeometric series, and it is from this fact that the series they define is called a hypergeometric series. It's a generalization of a geometric series. Okay. Okay. Then next, it's Riemann, who studied the relationship between hypergeometric series and differential equations. Okay. So a 2f1 hypergeometric function satisfies a second-order linear differential equation. And, you see that it has 3 regular singular points and a 0, 1, and infinity. So differential equation of this form is called a hypergeometric differential equation. Okay. So when such kind of differential equation is given, that we are given a point, then we can look for the solutions around that point. Now, of special interest is what happens when that point is at a singular point. Okay. So if we look at a singular point of 0, then we find out that 2f1 abcz is a solution of this differential equation at 0. Okay. And so that is the case if c is not a negative integer. So if c is a negative integer, differential equation makes sense. But this hypergeometric series does not make sense. But so if that's the case, then we write c as 1 minus m when the m becomes positive integer, and then we can find a solution which is expressed in terms of M and also the hypergeometric series. Okay. And we know that as a second-order linear differential equation, there are two independent solutions. So the second solution at around 0, well, it's also a hypergeometric series. But now here you have a factor z to the minus 1 minus c in front of 2f1 function. Okay. And similarly, at other singularities, at 1, you will get a solution which is expressed in powers of 1 minus z for both of them. And then infinity, you will get a solution expressed in terms of z to the minus 1. Okay. So the hypergeometric series actually recovers quite a bunch of the familiar functions. And because it's defined as infinite series, so the interesting question is that to which function it converges to. For instance, we can recover log 1 plus z, okay, as a hypergeometric function, or arc sine, or some kind say we have like this 1 minus z to the 1 minus a. Okay. And the interesting thing is that when does this infinite series converges to an algebraic function? And this was studied by Schwarz, and he gave a criterion for this to happen in the 19th century. Okay. And I think at the beginning people are interested in hypergeometric series partly because it covers a lot of the classical functions in analysis, such as the Bessel functions, Kummer's function. So they appear as a limit of the hypergeometric function. And also is that if we are given a second-order linear ODE with 3 regular singular points, then when you take any solution, you can express that using 2f1 hypergeometric function. And usually there's more than one ways, as we can see before, that at each point we have solutions which are expressed in terms of hypergeometric functions. But then in the region where the solutions both exist, then there are linear relations among them. So there are lots of relations among hypergeometric functions. Okay. And the last property here is that many orthogonal polynomials, such as Jacobi polynomials, Legendre polynomials, and Chebyshev polynomials, and they can also be written in terms of hypergeometric functions. Okay. So the connection with more modern subjects, such as modular forms. Okay. So let me first briefly explain what is modular form. So we have the group SL2R, X on the upper half plane by fractional linear transformations. Okay. And if we take any, say, discrete subgroup of SL2R, that gamma X on the upper half plane, and then I look at the orbit space, okay, which is a gamma upper half plane mod gamma, and if gamma is not co-compact, then we compactify it by adding cusps. Okay. So we end up with a Riemann surface. Okay. Or it's a curve defined over a complex field. Okay. Now let's consider the group gamma such that this curve has genus 0. Okay. For instance, we can take this group to be SL2Z, or say gamma 2, which is a subgroup of SL2Z, which consists of matrices which is congruent to identity modulo 2, or more generally an arithmetic triangle group. Okay, we'll see some examples later on. Okay. So, so these are all genus 0 groups. So that means that this orbit space X gamma is isomorphic to projective line, over complex stuff. Okay. So that means that on this orbit space, there is a meromorphic function with a simple 0 and also simple pole, which is a bijection between this curve and the P1C. Let's just choose fixed one, call that a lambda. Okay. So normally we use a tau as a variable for the upper half plane, and we use z as a variable for P1C. So that the z will be the lambda gamma of tau. So that's the relationship. Okay. So when we are given a group, we are interested in the functions on this orbit space or related to the group. So when if we are actually interested in holomorphic functions. If we look at holomorphic functions, then we only have constant functions. So that's not interesting. And other kinds of holomorphic functions that shows up that so it's not exactly invariant under the action of gamma, okay? But it has this relationship. So you take an element A, B, C, D from the group gamma, you look at F at the gamma of tau, so that's A tau plus B over C tau plus D. You compare that with the value of F of tau, and the ratio is a C tau plus D to the K. So when that thing happens, we say this holomorphic function is a modular form of weight K. So K is here. Okay. Yeah. So, and the interesting thing about the modular forms of a given weight is that it has a finite dimensional vector space. And when usually in number theory course, we study the other properties, that's Fourier coefficients and so on. But there's one important relationship is between the modular forms and differential equation. Okay. So if we take a weight K modular form for this group gamma, okay. So as a function in the variable tau, it doesn't have nice differential properties. But if you view that as a function in z, so instead of see that as a function on the tau plane, you see that as a function in P1C, then as a function in the variable z, that it satisfies a linear ODE of degree k plus 1. And so everybody, when we fix a group gamma, we have this fixed differential equation, then all the forms of weight k will satisfy that differential equation in the variable z, okay? And that equation has algebraic coefficients. So in particular, when that degree k is equal to 1, so we are looking at a linear ODE of degree 2, okay? And if that ODE, well, happens to be the hypergeometric differential equation, and if the initial conditions is correct, then we can express weight k, weight 2, sorry, in this case it will be weight 1 modular form as a 2f1 function. Okay. So I'll give you some example. For instance, we take a gamma to be SL2Z, and the standard map from the x mark gamma to x gamma to the P1C is the J function, and certainly 1728 over J is also a function with a simple zero and simple pole. Okay, so if we use that as the map lambda gamma, then we take the 2f1 with parameter 1/12, 5/12, and 1. Okay, then evaluate that as 1728 over J, and that function is the standard modular form of weight 4, E4 for SL2 gamma, taking fourth root. So superficially, that's a form of weight 1, but we know that SL2Z doesn't have a form weight 1, so we take fourth power, then this is legitimate relationship. Okay. Yeah. And second equation, example is where gamma is equal to gamma of 2, and the standard parameter, this lambda gamma we choose is the we take the Jacobi theta function, theta 2 over theta 3 to the fourth power. So theta 2 is taking the e to the 2 pi tau raised to the odd number squared, okay. And theta 3 is e to the 2 pi tau raised to n squared over 2. Okay, so suitable normalization. So then in this case, there's a 2f1 at 1/2, 1/2, 1, using this lambda. So we get weight 1 form. That weight 1 form is this theta 3 squared. So this one is legitimate. Okay. Okay. And the third example is a group gamma. It's what we call the arithmetic triangle group. Okay. So arithmetic triangle group means that we look at a group which is generated by 2 elements. The first generator has order E1, second generator has order E2, and the product has order E3. Okay. So each fundamental domain, well, has 3 sides. Okay. Say if you look at fundamental domain for SL2Z, it is 2, 3, infinity, and sometimes you'll get just the co-compact X gamma. Okay. So in this case, Yifan Yang gave a basis for the space of all the forms of all weight greater than or equal to 1. Okay. In terms of chosen lambda function and a suitable 2f1 function where the parameters A, B, C are expressed in terms of the order E1, E2, and E3. So these are the examples of connections between modular forms and hypergeometric function. Okay. So now let's generalize it. So from 2f1, where we take a 2 Pokehammer symbol product of them over 2 of them, we can, well, extend it to taking n such complex numbers, a1 to an. We take the parentheses r, then taking product, and the denominator will be the b's, and times z to the r, and then make a series. So from the viewpoint of power series, we certainly can define the generalization nfn minus 1 hypergeometric function this way as long as it converges somewhere. Okay. But since I'm also interested in the arithmetic viewpoint, so this nfn minus 1 is analytic viewpoint. Since I'm also interested in arithmetic, so I'll be more careful in choosing the parameters, AIs and the BJs. So, and we are going to choose this AI and the BJ with the non-zero rational numbers. Okay. And so we put them together and call that set a hypergeometric datum. So it consists of 2 sets of the, each one has n elements. So for the second set, beta set, the first B1 we always assume is equal to 1, just like the 2F1 we have seen here. So the missing here is a 1 that usually people don't write. Okay. And in this case, a hypergeometric datum is called a primitive if AI minus BJ is not integer. Okay. So I will say a little bit why we make this assumption. Okay. Then, so on the complex plane, when we define the hypergeometric function associated to this datum, okay, as we have here, this nfn minus 1 function, it satisfies an nth order linear ODE with 3 regular singularities as 0, 1, infinity, just like the 2f1. Just we change 2 to n, so we have that. Okay. So that means that if we pick up any complex number other than 0, 1, infinity, then we can solve for this second order, this nth order ODE, and we get n-dimensional solutions. Okay. So for each such point, we have a collection of n-dimensional solutions. As we move all these points around all the complex numbers except 0, 1, infinity, then we put them together, then we get a sheaf on the P1C minus 3 points. So this sheaf has rank n because on each fiber is n-dimensional space. And this sheaf usually is called a local system. Okay. And the assumption that HD is primitive means that this sheaf is irreducible, whatever it means. Okay. Okay. So an important thing about this situation is that in this case, we have a so-called monodromy representation. So let's think of it this way. So let's take a point, complex point other than 0, 1, infinity. We say that the solutions through this point is form an n-dimensional space. So take any solution, and also we take any closed curve starting from this point and come back to this point, okay? So which this curve is on the P1C minus 3 points. Okay. So I start from this solution, I analytically continuate this solution along this curve. When I return to this point, usually I would arrive at a different solution. So then from one solution, I come up with a different solution. So that gives us action of, we view that as an action of this loop on applied to the first solution with the image being the second solution. So this, we call that a representation of the fundamental group. Okay. So this is analytic setting. From the data, we have the hypergeometric function, and we have local system of rank n on P1C minus 3 points, and there's a monotomy representation of the fundamental group. Okay. So next, we look at the algebraic story or arithmetic story. Okay. So since our AIs and BJs are rational functions, so they have denominators. That's called the least common denominator, m, and so we think of that as the level of this that hypergeometric datum. Okay. So now, algebraically, we also are going to mimic what we saw on the complex, on the C over C case. So in this case, we fix any choice of prime number called L. Okay. Then the cats introduce an L-adic rank n hypergeometric sheaf. Okay. And so now, before the sheaf was on P1C minus 3 points, okay, 0, 1, infinity. And now the L-adic sheaf is on the what called a group GM. So GM applied to C means that C cross. It means that all the complex numbers other than 0 and infinity. So it just has one extra point at 1. Okay, so that's a different. Okay. And so first of all, we have this sheaf. And secondly, that before we had a monotomy representation of a fundamental group. Now we have a representation of the Galois group. So the Galois group over the cyclotomic field joining m through the 1. That's that m. Okay. So I'm just going to call this Galois group G of m. So m tells you the level. Okay. So and so we have, so just very similar to what we saw about the monotomy action. So now for this Galois action, again we pick up lambda, which is in the field, which is a non-zero element in the field. We call it lambda. Then we also have the action of Galois group on the fiber at that point lambda. Okay, so that representation is, we call that the row attached to the data HD at point lambda, which is L-adic. Okay. So to describe a Galois representation, we talk about what is the Frobenius trace. Okay. So in this case, Frobenius trace is given in terms of the hypergeometric character sums. And these hypergeometric character sums themselves are the finite field analog of the NF n-1 that we saw analytically. So I'm going to give you an example of this thing. Okay. So this was initially studied by Katz and then later developed by Fuselier in the big memoir by Fuselier, Long, Ramakrishna, Swisher, and Tu. Okay. So let me say a few words about the. So we saw the analogy, but there's also some difference. Okay. So the first difference is that when on the complex side we look at the hypergeometric function, it's independent of orders, AIs and the BJs. But for representation, it does depend on the order. But on the other hand, it's independent if we permute the columns. So if we permute columns AI, BI with a column AJ, BJ, then the representation stays the same. Okay. And secondly, for the Galois representation, it only depends on this numbers modulo z, so only the fraction part. The integer part is independent. Okay, so that is different from the complex case. Okay, so then after we understand that, then we call a data is defined over Q if these columns remain the same when we multiply that by any integer which is a co-prime to M, well, modulo Z. Okay. Yeah. So in the case that a datum is defined over Q, then the Katz representation, which was originally for Galois representation of the cyclotomic field, can be extended all the way to the Galois group of Q. So the base field goes from cyclotomic field to Q, or you can think of that joining zeta 2, so which is the Q of -1. Q joining -1 is the same as Q. Okay. So the key point here is that when the data is defined over Q, then the representation originally defined for the Galois group of the cyclotomic field can be extended further to Galois group all the way down to Galois group of Q. Okay. And there are several such extensions. Okay. So one such extension is very special. It's studied by Boykers, Cohen, and Melit. Okay. And we call that BCM representation attached to the datum HD. Okay. And to describe, so this BCM representation itself was defined geometrically. Coming from algebraic geometry, they found some varieties, etc. So they came up with representation. Later on, they showed that representation actually extends Katz representation. Okay, but BCM representation is what we are going to use. Okay, so. As before, so this BCM representation is a representation of Galois group Q, so it's, described in terms of traces. Okay, so a trace is given by a hypergeometric character sum. So let me just give you some example. Okay, so if the data is defined over Q, and if this prime P, well, it doesn't divide the level. Okay, then when this level M divides Q minus P minus 1, then this hypergeometric character sum is defined in this way, which looks very complicated, but actually which is exact analog of the NFN minus 1 hypergeometric function. Let me explain this a little bit. Okay. So the definition here uses a Gauss sum. Okay. And before, it uses a Poker-Hammond symbol, and recall that a Poker-Hammond symbol itself is a quotient of Gauss gamma function here. So each Poker-Hammond symbol is a quotient of a gamma value, gamma A plus R over gamma A. The finite field analog of gamma function is Gauss sum. Okay. And this A plus R and the A business in the analog becomes the exponents here. So this AJ is that A. So this AJ here and the K, this is the replacement of A plus K. The bottom is A, so the quotient of gamma. Okay. And the B part lies in the denominator. But the Gauss sum has the property that if you replace a character by its inverse, then you can flip the order. So this part corresponds to the Poker-Hammond symbol of BJ K part. Okay, so then the same, you take product, and instead of the summing over all, infinite sum, now for finite field case, it's only finite sum. So this is very similar. Okay, so I give you some flavor of the hypergeometric character sum, and the important thing is that when the data is defined over Q, we can extend the Katz representation to the BCM representation, and that BCM representation is characterized by the Frobenius trace at the prime P, and you can see the Frobenius trace of prime P is given by the hypergeometric character sum. except that in front of it there is some modification. Okay, so this hypergeometric character sum itself is a rational number, and in this case we need to multiply by power of p to make it integer, and so the m here is the number of integers which show up in the second data beta. And in front of this are the signs, plus minus ones. Okay, so basically we could just say that the BCM representation has Frobenius trace at Frobenius P is given by hypergeometric function. Okay, and another thing I like to point out is that this lambda runs through the Q cross, points in Q cross. Okay, so when lambda is not equal to 1, this representation has degree n, but at 1, this new extra point has degree 1 less at n minus 1. Okay. I'm just seeing how much time I have. Yeah. Okay. I was going to give you an example so that you feel a little bit better, but I think I have to go quickly. So if the data, it choose the alpha is order 1/2, beta is order 1 with length 3. Okay. So in this case, the level is equal to 2, and the cyclotomic field itself is the Q, so that the CATS representation agrees with the BCM representation. Okay. And in this case, the hypergeometric character sum can be explicitly written down this way using the quadratic character modulo P. Okay. So as you can see that we have explicit formula here, and with quadratic character, this strongly suggests that we should consider the variety defined by s squared equal to this polynomial inside, xy times x minus lambda y times y minus 1 times 1 minus x. Okay. So this surface is a double cover of the P2C, and its smooth model is a K3 surface. Okay. It has a good reduction at P for this P which doesn't divide 2 and the denominator of lambda. Okay. And so since it has a good reduction at P's, we can modulo P and count how many solutions there are. We find out that the number of solutions is equal to P squared times this hypergeometric character sum. Okay. Then the question is that, if you, for people who are in geometry, that we understand that when you count the number of solutions mod P, you know that the contributions, you look at the zeta function from various pieces of cohomology. Then the question is from which piece does this hypergeometric character show up? Okay. So the answer is that it's coming from the H2 of this surface with the analytic the constant sheaf. Okay. So this H2 itself is a 22-dimensional space. Okay. And when lambda is not equal to 1, the algebraic cycles spans a 19-dimensional space. Okay. And so the remaining 3-dimensional space is spanned by the transcendental lattice. So this piece actually comes from the transcendental lattice. Okay. That's the contribution it comes from. Okay. And when lambda is equal to 1, then the algebraic piece has dimension 20. So the transcendental piece has 1 dimensional less, so the representation is 2-dimensional. So this gives us a very concrete geometric realization of the CATS representation, which originally was defined in terms of hypergeometric sheaf. But here in this case, we see that where it is realized geometrically. This is coming from the transcendental cycle sits inside H2 of this K3 surface. Okay. Yeah. And another interesting thing is that when lambda equal to 1, we know that the the representation we see is a two-dimensional space. When the two-dimensional space and the representation of a Galois group of Q, a very immediate question is that whether it has anything to do with modular form. Okay. And the answer there is yes. So, and the way to see that is that this K3 surface, when lambda equal to 1, has a different way to see that. It is birationally isomorphic to an elliptic surface over a genus 0 curve. Okay. So then this particular representation at 1 can be realized on the H1 of this curve with a fancier sheaf coming from constant sheaf from the elliptic surface and pushing down. Okay. And the bottom line is that when at lambda equal to 1, you can find out that the Frobenius trace at P is equal to the P's eigenvalue of the Heck operator on this weight 3 modular form eta 4 tau to the 6. So that means that this representation at lambda equal to 1 corresponds to the modular form eta 4 tau to the 6. This is what we call the modularity. Okay. So then what I'm going to do now is the joint work with Lin Long and Fountain 2. Okay. So what we did is that, as I pointed out, that hypergeometric functions satisfy lots of identities. There are thousands of identities they satisfy. So what we do is that we pick a very special identity. It's called a Whipple identity. And that formula relates 756 to 453. Okay. So you can think of that so this particular choice of 756 degenerates to 453. 7F6 degenerates to 4F3, okay, but with a bunch of the gamma thing in front, okay. But this identity here holds when both sides terminate. That means that one of A, E, F, G should be a negative integer, okay, or non-positive integer, okay. So we are not going to do this in general. We are going to take a more special case, namely, so the data, the two data, datum alpha and the beta shows up here has a property that AI plus BI is equal to A plus 1. Okay, so if we know the top row, then we immediately know the bottom row. Okay. But we are going to specify even more is about the columns, the relationship. Okay. We want to specify in the case that we call the data is so-called a self-dual. So if I choose A to be 1/2, okay, that determines the second column, and C will be C, and D will be 1 minus C. So that's the self-dual part. Then F, and that will be F, and the G will be 1 minus F. Okay. Now E is trickier. So E here we will choose as 1 minus P over 2, and the bottom will become 1 plus P over 2. Okay. So in this particular case, then we have also have the identity which carries on. Okay. So we want to give a Galois representation theoretic interpretation of this identity. This identity is a special value. So there's a hypergeometric function at the variable z equal to 1, okay, with the AIs and BJs chosen as we just said. Okay. So we want to interpret this particular value at 1 here, which is related to the Galois representation at Frobenius at the P. Now, one thing I didn't say is the Galois representation of Frobenius of P depends only on those rational numbers modulo P. So when you mod P, then this P will disappear, so that becomes 1/2 on top, okay, and 1 at the bottom. So then that's what we are going to do, okay. And also, when this 5/4 is congruent to 1/4 modulo Z, so from the Galois representation thing, they have no contribution, so we are going to ignore that. Okay. So after we have noticed this, that means that from the 7F6 part, we drop out 1 column. We come up with this the first set, which has length 6, okay, and the beta will be such that the corresponding value added will be 3/2, okay, and that also determines the second datum. Okay, so we want to reinterpret that complex identity using the Galois representations associated to the first datum, which has length 6, and the second datum, which has length 4. Okay. But so we extract these two datums from the original Whipple identity, but we are going to drop the condition that the original condition said that it holds only when the hypergeometric function actually terminates. We're going to drop that condition. We do not assume that to have some negative integer. Okay. So here is our first conclusion. Okay. So let me show it again. So here, so the relationship from the complex values here is the 7f6 related to 4f3, but there's a p here in front. Okay. So then the left-hand side here, we are going to associate that with the representation associated to the first datum. Okay. And 1 here comes from the value that because the hypergeometric identity here is at lambda equal to 1. Okay. Sorry. Okay, so to the first datum, we have the CAS representation. To the second datum, we also have a CAS representation. They're both at lambda equal to 1. Okay, and each will be for the Galois group and for over cyclotomic field of its own level. So we are going to choose a level slightly bigger. We call the n. So the n is either m or twice m. Okay, we're going to restrict both representations on the Galois group over the cyclotomic field, joining n through the 1. Okay. So originally, at the complex side, you see that the values degenerate. From the representation point of view, it becomes that, so the representation associated to second datum, well, we twist by the cyclotomic character in front because of that p in front. So then it's that this representation attached to second datum is a piece of the representation attached to first datum. Okay, so there's a complement piece. Complement is a two-dimensional representation. Okay, so the semi-simplification here means that both sides have the same Frobenius trace. Okay, but if the first datum is defined over Q, then the representation itself is semi-simple, so we can, well, then we can ignore that semi-simplification. So we just have that decomposition. So once again, so the complex side, that's the identity. So 756 special value related to 4f3 special value. So this identity, from representation point of view, is the representation associated to second piece. Here is a piece of the representation associated to the first datum. So among all the pairs which is allowed, we are particularly interested in the case that where pair is such that the first datum is defined over Q, and there are only 7 such pairs. Okay, so then let's just choose these 7 pairs. Okay, then with these 7 pairs, we look at the second datum. Well, it is primitive for all, but it's defined over Q only for the first 5 pairs. For the last 2 pairs that are this data itself is not defined over Q. Okay. And also for the 7 pairs, the level for the first datum and the level for the second datum, they agree, so that's nice. Okay. And so the CAS representation that we know that for the attached to the first datum has degree 5. attached to the second datum has degree 3. Okay. Now, because the datums of for the is defined over Q for the first datum, so we know the CATS representation can be extended to the Galois group of Q to become the BCM representation. And for the second datum, for the first 5 pairs, well, we can extend. But it turns out that for last 2, although the datums themselves are not defined over Q, but the representations can be extended. So the final conclusion is that for all the 7 pairs that are all both CATS representations can be extended to representation of Q. Okay. Now, since this representation, BCM representations, they arrive geometrically. Okay. So then the next question is the connection with the modular forms. Okay. Or what we call the modularity or automorphy. Okay. So for first, I just want to say that for the BCM representation attached to the second datum at 1, it's a 3-dimensional, and actually it decomposes a degree 2 plus degree 1. And the first representation attached to the first datum has degree 5, decomposes into degree 4 and degree 1. Okay. So we're going to study each piece. Okay. So for the second datum, H2, okay. And so then our conclusion is that this degree 2 piece actually comes from modular form. Degree 1 piece, well, comes from, also character, okay. So they are both modular, okay. And here we give a very explicit modular form that corresponds to this Galois representation, okay. So now let's look at the BCM representation associated to the first datum, okay. Because it's degree 5, as we said earlier, okay. And this 5 becomes degree 4 plus degree 1, but then even earlier we say that this degree 5 representation decomposes this the representation attached to second datum plus degree 2. This representation attached to the second datum splits into degree 2 plus degree 1. So that means that after we ignore that degree 1, then the degree 4 piece of the representation decomposes into degree 2 plus degree 2. Okay. So then we ask what happens to each of the degree 2 representation of the Galois group. Okay. So here is the precise answer. Okay. So as you can see that so the first piece here is a piece corresponding to that we call the extra piece, sigma sim. Okay. Okay. And because the other piece has the other piece because it has the twist by cyclotomic character, so all the traces will have a P sitting in front. So that is the second plus third. Second plus third together is coming from the representation attached to second datum. Okay. But one notice that when I said that when we extend the extension, okay, BCM is one extension, you may notice that for the piece which come from the extension of the second datum, actually the modular form here are not exactly the same as modular form we choose from the BCM extension for the second datum. Instead, it's coming from the second expression here. So they are related by quadratic twist. As we say that when you extend the representation, extension is not unique, so here it shows. So because this representation attached to the first datum decomposes as degree 2 plus degree 2 plus degree 1, when you extend it to Galois group Q, each reducible piece has its own extension. Okay, so that shows up in the data. Okay, not yet. So I think I will skip skip the schedule proof, but I go to the next connection. I think it's more interesting. It's a connection between periods and special hypergeometric values. Okay. So if we consider the elliptic curve, which is defined by y squared equal to this degree 4 polynomial 1 minus x squared times 1 minus k squared x squared. So to make an elliptic curve, k cannot be 0, cannot be plus minus 1. It can be any other complex numbers. Okay. So we think of this elliptic curve as a twofold curve of a complex. So the complex is referring to the x-coordinate. So when we are given the x-coordinate, there are two choices of y by taking square root. So that's a twofold curve. Okay. So on this elliptic curve, I'm going to just to choose a special closed path. Okay. So I will start at the point x equal to minus 1, so that y is equal to 0. Okay. Then I'm going to move the x from minus 1 towards 1. When I go towards 1 here, again, the y becomes 0. So when I move from the minus 1, 0 to 1, 0, so when I take an x, which is, say, in between minus 1 and 1, I have two choices of y. So first, I choose the plus branch. After I reach the 1, 0, when I go back to the minus 1, 0, I will travel along the lower branch. So I started from the upper branch, then I go back on the lower branch. So you see a circle. Okay. So on this elliptic curve, I'm going to choose a basis for the first round cohomology. The first one is the holomorphic differential dx over y. The second is the dx over y times 1 minus k squared x squared. So it is holomorphic everywhere except at the pole at infinity. Okay. So I take these two both one forms, we integrate along this closed cycle. This is called a period. Okay. So the first period, you see that it is value is a 2f1 and half 1 at a k squared, well, times 2 pi. The second period is a 2f1 and minus half 1 at k squared, also times 2 pi. Okay. So this is when I fix a k, I have this elliptic curve, I come up with these two periods for that elliptic curve. So now I'm going to vary this k. So as k varies, then this period becomes period functions. And these two period functions, they satisfy a differential equation. So the second period, well, it's related to the first period this way. You take first period multiplied by 1 minus k squared times its derivative times k times 1 minus k squared. So they are related by first order differential equation. Okay. And for modular form, a standard period is that you take this modular form, you integrate along the imaginary axis from 0 to infinity, but you also multiply by suitable powers of t, and that exponent runs from 0 to k minus 2 if this form has weight k. Okay. In the front, we have a suitable normalization. So this value here is the so-called the value of the L function associated to this modular form at r plus 1. Okay. And so the Lin has a very general conjecture, says that when this r, or this r plus 1, integers between 1 and the k minus 1, and these values here has very special arithmetic meanings. Okay. So for instance, if I take the f to be the eta 4 tau to the 6, this is a weight 3 form that we saw before, then we find out that its value at L function at the 2 is a 3f2 hypergeometric value, special value at 1. And the Zagier showed that if you take the modular form of weight 4 and for gamma naught 8, and that the L function at the 2 is also 4f3 at order 1/2, so 1. Okay. So in general, when we are given, say, a curve form, when we say it's a period, we also consider this form that we integrate along the closed cycles on the on x gamma. Okay. We also multiply it by tau to the exponent, which sits between 1 and 0 and k minus 1. Okay. So that's what we call the periods of modular forms. Okay. Now, for our special situation, we have the datum, this first datum of length 6 attached to CF particularly. So we look at the hypergeometric function, the value at lambda. Okay. So that's 1/2 C, 1 minus C, half F, 1 minus F. That's the first row. Okay. Then we compare that with the value of a hypergeometric function, 7F6, where we put back this 5/4 for 1/4. This was second column, which we deleted because we say from arithmetic viewpoint that they give the same representation. Now let's just install it, put it back here. The rest is the same as the first datum. Okay. So we look at this 756 at lambda. Okay. It turns out that the 7F6 at lambda is the 6F5 lambda value plus its derivative times 4. So this is very similar to the relationship we saw in the periods for elliptic curves. Second period is related to the first one by the first order differential equation. So because we have this, so we expect that this F lambda and 7F6 lambda should also be periods. Okay. And indeed, okay, for the case that CF is 1/2, 1/2, we have shown that this 6F5, all the 1/2s on the top row, all the ones on the second row at 1, it is indeed a period. For the modular form, this F weight 6, level 8, that's one which shows up before we. This one shows up here. Okay. Sorry. But we multiply by tau square. And we also, to say that it's a period, so we identify the form. We also identify the closed path. So closed path is from the 1/2 plus I over 2 to minus 1/2 plus I over 2. This is the hyperbolic geodesic. It is a closed curve for the group gamma naught 8. So that is a period. And likewise, the 7F6 itself is also a period. Now it's related to the form, weight 4 for the same group, but a tau in front. So all the hard work is to find the form and to find this path, so that to realize this hypergeometric value as a period. Okay. And there's similar but more complicated results for 2 other pairs. So thank you very much for your attention. It's very difficult. That's all we could do. There's some philosophy which thinks that they should, this hypergeometric value should be a period. Then you just have to find out what is the form and what kind of tau you put in here. You see this subtle change and along which path. Yeah. Yeah.
N-dimensional to the n-dimensional space, so then you can play the same trick.
I'm sorry, I didn't quite get you.
So for 2F1, you have a family of elliptic curves. And the first cohomology is two-dimensional. And you interpret that as solution space of the second order ODE. Now for n minus 1, the equation is of n order, so you will need some geometric object whose first cohomology is n-dimensional. So what is that?
I don't know.
And n may not be even, so it may not be a Riemann surface.
I'm just learning. I told you all I know. So it's but I think that I decided to talk about it because I find it's very interesting that hypergeometric function has connections to many subjects. Depends on your interest, and you find an angle to study it. Yeah. But there's a lot of geometry behind it. Yeah.
Any other questions for the speaker?
So you have E4 as a fourth power of hypergeometric function. What about E6? Is it also?
I don't know. See, normally people really write that as a 2f1 equal to fourth root of E4.
Yeah.
Because the second order corresponds to k equal to 1, and so wave 4 you take fourth root. Superficially it's a wave 1 form, except that it should not exist. Yeah. So you're asking me whether you take 6 root of E6 or
No, not necessarily.
Not necessarily.
E6 is expressed in terms of hypergeometric function.
right. I'm thinking whether Ivan-Yang, I think you can use Ivan-Yang theorem, because Ivan-Yang applied to a triangle group triangle group has unit 0, and this SL2Z is a group with 2, 3 infinity, so it is a triangle group. And so I think so. I think Ivan's formula can tell you how to, his formula will tell you how to write E6 in terms of lambda and hypergeometric function, 2f1. But he uses the two 2f1s. Yes, you can explain. Yeah, use his theorem. But I suppose it's not as neat as what we have seen for E4. Yeah, I think usually in general it involves two f1s. The parameters are sort of dual to each other. I only said that expressed in terms of E1 into E3, but actually there are two behind it to build. Good question. Makes me think.
So we know that E2, E4, and E6 satisfies a set of first order ODEs.
Right.
That's said by Ramanujan. So is that related to the second order ODE satisfied by 2f1?
In front, I do not know. But there's a very interesting paper by Zagiev, which I strongly suggest, where he find also a lot of connections. Yeah. Also related to the mirror symmetry. I think beautiful in geometry would be more interesting. Just I didn't understand it well enough to present it. but hypergeometric value also shows up there.
Any other questions? Something that just talk, take our speaker again.